A compass looks almost too simple to matter: a needle, a dial, and a few letters. But that simplicity hides a powerful idea. A compass gives you a stable reference direction when everything else feels unstable, whether you are at sea, in a forest, or in a city where landmarks disappear. Before tools like this, navigation relied heavily on memory, stars, coastlines, and luck. The compass changed that by offering a portable orientation system you could carry anywhere. Instead of asking, "Where am I going first?" people could ask, "Which way is north?" and build every other decision from there. That shift sounds small, but it is profound. Direction became measurable. Movement became intentional. Routes became repeatable. A compass did not just help people avoid getting lost. It made long-distance planning more reliable and therefore more ambitious. Trade expanded, exploration accelerated, and journeys became less dependent on perfect weather or perfect visibility. In short, the compass turned uncertainty into geometry. At its core, a traditional magnetic compass works because Earth itself behaves like a giant magnet. A magnetized needle is free to rotate on a very low-friction pivot. When you hold the compass level, the needle is pulled by Earth's magnetic field and aligns with it. The north-seeking end points roughly toward the planet's magnetic north region, while the opposite end points toward magnetic south. The key word is roughly. The needle is not detecting the geographic axis of Earth's spin directly, it is responding to magnetism. This is why the needle can wobble for a moment, overshoot, and then settle into place as friction and oscillation fade. Better compasses use jewel bearings or refined pivots so that settling is faster and readings are steadier. Think of the needle as a lightweight weather vane, but for an invisible magnetic wind. You are not forcing the needle to point north. You are allowing it to reveal the field that is already there. That passive behavior is exactly why the instrument is trustworthy when used correctly. To use a compass well, you need to speak its numeric language, not just its letters. Most compasses are marked in degrees from 0 to 360. North is 0 degrees, east is 90, south is 180, and west is 270. Those numbers allow you to describe a direction precisely as a bearing, sometimes called an azimuth. Instead of saying "go a bit to the right of east," you can say "travel on 105 degrees. That difference matters because language is fuzzy and numbers are reproducible. If a route is written as bearings and distances, another person can follow it with far less ambiguity. Rescue teams, surveyors, soldiers, hikers, and sailors all benefit from this precision. The compass becomes more than a north pointer, it becomes an angle measuring tool for action. You can take a bearing to a landmark, compare it to map information, and confirm whether you are drifting off course before mistakes become expensive. In navigation, small angular errors compound over distance. Degree markings are what keep small errors from becoming major detours. Here is the critical complication most beginners miss: magnetic north and true north are not the same thing. True north points to the geographic North Pole, the axis around which Earth rotates. Magnetic north points to the direction of the local magnetic field, which depends on Earth's magnetic structure. The angle between these two directions is called magnetic declination, and it changes based on where you are. In one region, the compass may point several degrees east of true north. In another, several degrees west. If you ignore this difference, your route can be consistently wrong even when your compass handling is perfect. Over short distances, the error may feel minor. Over long distances, it can move you far away from your intended destination. This is why maps often print local declination data and why many field compasses include an adjustment mechanism. The compass is not broken when it disagrees with your map's north. It is measuring a different north reference. Good navigation is really about translating between reference systems. Declination is not only location-dependent, it is time-dependent. Earth's magnetic poles drift gradually, a long-term process known as geomagnetic secular variation. That means the declination value for a place in 1 year may not be accurate years later. A map can be topographically excellent but still mislead you if its declination note is outdated and you never correct for that drift. This is one reason professionals treat maps as dated instruments, not timeless truth. They check publication year, update data when possible, and verify local magnetic information before relying on bearings. Conceptually, this teaches an important lesson. Navigation tools are not static facts, they are measurements tied to changing systems. Earth's magnetic environment evolves, and your workflow has to evolve with it. Even in the digital era, this matters because phones and GPS devices still depend on models and sensors that require calibration and updates. The old compass problem of changing north never disappeared, modern interfaces simply hide it better. The compass also has a deep historical arc. Early magnetic direction tools appeared in ancient China, initially associated with divination practices during the Han period. Over time, magnetic orientation moved from ritual context into practical navigation, especially by the Song era. That transition from symbolic meaning to operational utility is a recurring pattern in technology history. People discover a phenomenon, assign cultural significance, and eventually engineer it into infrastructure. Once magnetic direction became useful for travel, its impact expanded beyond one region. Records of compass use appear later in Western Europe and the Islamic world, where navigation needs in trade, scholarship, and maritime movement created demand for reliable orientation tools. Importantly, inventions are rarely single-moment events. What we call the compass is a chain of refinements, adoptions, reinterpretations, and standardizations across cultures. The core principle remained magnetic alignment, but its social role changed dramatically, from interpretive device to essential navigation technology that supported broader networks of commerce and contact. Using a magnetic compass accurately requires technique, because nearby materials can distort readings. Steel objects, electronics, speakers, vehicles, and even reinforced concrete can interfere with the local field around your compass. If the needle is influenced by a nearby magnetic source, it will still settle confidently, but to the wrong direction. Confidence is not the same as correctness. This is why field practice includes holding the compass level, away from metal, pausing for oscillation to stop, and cross-checking with terrain or secondary references. Instructors often teach repeated readings from slightly different positions to detect anomalies. If bearings shift unexpectedly over a few steps, interference may be the culprit. Operationally, this means compass use is both instrument reading and environmental judgment. You are not just reading a dial, you are evaluating measurement conditions. The better your measurement hygiene, the more trustworthy your navigation decisions become. A compass is robust, but not magical. It rewards disciplined handling and punishes casual assumptions. Modern navigation expanded the compass concept rather than replacing it outright. Gyro compasses, for example, use rotational physics and are not pulled by magnetism the same way a needle is. They are valuable in contexts where magnetic distortion is problematic, especially on large vessels. Magnetometers in smartphones act as electronic compasses, often fused with accelerometers and gyros to stabilize orientation estimates. GPS adds position data, helping systems infer heading when movement is present. But each method has trade-offs. Magnetic sensors can be disturbed. Gyro systems can drift and need correction. GPS can degrade in dense urban areas, indoors, or under jamming conditions. Sensor fusion helps because no single method is perfect everywhere. The classic magnetic compass remains relevant as a low-power, independent reference that does not require satellites, batteries, or network access. In risk terms, it is a resilient fallback and often a primary tool in remote environments. Old technology survives when it solves a core problem elegantly under failure conditions. A practical map and compass workflow turns theory into reliable movement. First, orient your map so its north matches your corrected compass north, accounting for declination. Then identify your current position using terrain features, paths, or known points. Next, draw or imagine the line to your destination and read the corresponding bearing. Set that bearing on your compass, align the needle, and choose a visible landmark in that direction so you can walk in segments rather than staring at the dial nonstop. Periodically recheck to manage drift, especially after obstacles force detours. If visibility is poor, shorten movement legs and increase verification frequency. This process sounds methodical because it is. Navigation failure often comes from skipping small checks, not from lacking intelligence. The compass workflow reduces cognitive load by converting choices into repeatable microsteps. You do not need constant certainty about the whole journey. You need local directional certainty repeated enough times to produce global accuracy. That is how simple tools enable complex travel. There is also a broader philosophical reason the compass still matters. It represents a class of tools that provide orientation before optimization. Today, many systems optimize routes, estimate arrival times, and automate turn-by-turn decisions. But if that layer fails, orientation is what remains. Knowing direction restores agency. With a compass and map literacy, you can recover from uncertainty instead of waiting for external systems to recover for you. This mindset applies beyond wilderness travel. In aviation, maritime operations, emergency response, and field science, teams maintain analog competencies because resilience depends on independent reference frames. The compass teaches an enduring principle: robust systems combine precision with simplicity, and convenience with fallback. A tiny needle cannot tell you everything. But by anchoring you to a dependable directional frame, it enables almost everything else in navigation to function. That is why the compass is not just an old instrument. It is a compact lesson in how humans turn invisible natural patterns into practical power. If you found this helpful, please like this video and subscribe for more explainers.